reinstall and redo everything.
That's what Ken also did. So I think I probably reset your password or something. Did you change your password in the last 1 month?
I didn't have to change it. I just had to
Reset it.
I did the same thing with the Java.
I see.
Because I have it going, or not Java, the Linux, because I have my computational stuff through Linux. And it kept on freezing. It kept on disconnecting.
In my case, it was the password because of the, at least I thought it was for everyone in this university, but at least I get an email every December saying that change your password. So I think it expires every 1 year, something like that. So I don't know what happens.
Yeah, they haven't
But
sent
it
me
worked.
anything yet.
But did it work eventually?
I got it to work.
But you had to.
For that one, I updated Linux. It went from 20 to 20.1 or something like that.
See. So you had to update the whole of your Linux for Wi-Fi to work.
And then it started working.
Okay. Seems like a big.
Well, it wasn't that hard because it
Just updated it.
Yeah, it didn't apply. It kept on running kind of odd, and when I finally looked at the messages for alerts, it said there was a new version.
Okay.
There's certain things I like about Linux. It's like, my computer at home, I installed the VPN and I used one method of installing it. And here I went to the same page, different set of instructions.
So what do you like about it? You don't like, you said, or you?
I like a lot of things about it. I do like it's cleaner and faster than Windows.
Of course, yeah. Architecture is clean. Yeah. No doubt Linux has a lot of, but the problem is it's not at all friendly with the commercial devices.
No.
It's not at all. So it becomes a huge challenge. Like for example, this camera, if I were to hook it onto a Linux, there is a very good chance that it won't be detected. So,
I had to buy a second network adapter for my computer at home.
So that becomes the big difference. Oh, Luke.
Hello.
Yeah. So I should maybe move the camera so that you can see others. Hey, Moses.
How's it going, man?
Good, how are you?
All right.
So we have Ken is the new student.
Hey Ken. And Moses.
So that's Moses and that's Luke on the screen.
Nice to meet you.
Oh, we can change the one. Can you speak once more, Luke? For the volume?
Can you hear me?
We heard him.
It was okay.
Yeah.
Michael?
Hi, how's everyone?
Good, yeah. So, Moses is not on the screen. So, Aliyah? Again, Ken is a new student, so he's, yeah, so, introduce each other again. So, are you the only new student this semester?
So, yeah.
So, I think get to know each other. So for those who are online, I think you guys know how to get to my homepage. From there, reach the syllabus somehow. And because I cannot pass the syllabus through online, few limitations still apply. That's pretty much identical to what we had last semester. You guys reach the place, Michael?
I have, yes.
Talia?
Yes.
We get the and syllabus and the, what is the other thing? Homework, right? That's the two things. They have, I think, Ken, you were there in classical mechanics, mode, everything remains the same. And others, you have been in the first semester, so everything remains the same, except probably the distribution of points. I don't remember, what was it in the first semester? The distribution is homework. Yeah, homework, 40%. And was this different in classical mechanics, Ken? Do you remember by any chance? It looks the same, right? Okay. So yeah, 40% homework, midterms, two midterms. Yeah, that's it, slightly different. Last
I
time
don't
we
think we
had.
had quizzes though.
Oh, I changed it, extra credit, I made it quiz.
Okay, good.
Oh, okay.
Because someone in my evaluation wrote, why call it extra credit when there is 10% points associated with it?
Okay.
I thought it was reasonable to
Yeah.
change the name.
They actually made it more, it's 10% instead of 5.
Yeah, I thought it was
Oh,
five.
it was five.
last
Okay,
time.
okay. Yeah, but you guys saw the drill, right? It should be relatively straightforward. But do you think it was? Oh, before, I don't see Jordan, but I did see him around. I think he's in the wrong place. Could you send a message to
Oh,
him? Do you
you
guys
saw
have?
him on campus?
No, I think I got a message on my email. I think he was trying to log in, maybe.
Okay.
Do you guys have access to?
I don't have anything with me then.
Oh, yeah. If someone has Jordan's number,
Oh, I
just
can text him.
And he was at the TA meeting, so
yeah.
he's around.
Yeah, so I think he might be in the wrong place. Just ask him, check the room. Yeah, so it reminded me because Jordan is the one who said, someone who was saying that the quizzes become like too hectic, like every day there's a quiz, and uploading is, like it probably is, after a while in the middle of the semester, there's too much stuff going on. But I thought it's still, I kept it, maybe, yeah, I didn't realize I increased it to 10% and it was 5% earlier. But I think it's a reasonably easy thing to get points from with a very limited amount of effort you put in. So I used it for curving also, so I thought it's okay. Any comments? I'm open for, at this point, we can even change it if anyone thinks that that's a bad move to make it 10%. Anyone?
There's just more incentive to do them.
Okay, yeah. So it doesn't seem like that might hurt. All right. Okay. Good.
Jordan said he is trying to join. I told him a different link, just to check a different link.
Okay. Okay. Yeah, everything else remains the same. Only 2 midterms instead of 3 like last time, so that's different. About the second semester, so it should. Usually I do have two exams. Last time it was 3 because it was the first time it was online, so I didn't want to take a chance. I think now we have learned it a little bit, so it seems like it should be okay. Okay. Oh, anything else? That's all I want to talk about service.
I have a question on the,
Yeah.
you, on the equation 1, you circled
Yes.
the cube.
Yes, that's a typo. So good, good point. Oh, I
I
understand.
didn't know if it was supposed to be just eliminated entirely or supposed to be squared.
Just 3, replace 3 with 1. Yeah.
Okay.
I'll write that up before I move this. And you guys also said you would like to zoom in if it helps. That's
There it
Jordan.
is.
That was it.
So yeah, Jordan, you came late. Later, you have difficulty getting on. Everything remains the same, I guess, except there are only 2 midterms this time, and there is the quiz. Extra credit is called quiz this time. Only the name changes, but everything remains the same, and it is 10% apparently.
Okay.
Instead of 5. And homework 1. Homework 1 is due next week. And in the homework, there is a typo. It is showing this as 3. Strike this 3 and make it basically 1. Strike it. That's it. And that is a midterm, which is pretty far away. So February 23rd. Okay. Is everyone here? Do you guys think so, right? Yeah, I think Avinash is not going to be. I think he said
And Ahmed is
Khaled.
Khaled.
Khaled,
Yes,
right? Yeah, he also said he will be meeting with me once in a while, but I think he's not
Gotcha.
attending the course as such here. Yeah. So yeah, I guess all of this. Okay. So this semester we wanted to do magnetostatics. We did a lot of electrostatics last time. So broadly speaking, what we'll do is about a month or so we will do magnetostatics, and then we will do dynamics in the sense we'll remove the constraint of statics. And Ken, I forget. This is part 2 of a course, right? And you're enrolled in it. It didn't strike me. Yeah, you should meet me, right? It might not be okay. I don't know. Have you taken electrodynamics before?
I took it at my undergrad school.
Undergrad.
Now, but this looks very familiar. I can do it.
Yeah, still, you need we should talk. Okay, after the class, maybe if you're available. Yeah, yeah. Okay. Yeah, so broadly speaking, we will do three things maybe I can say. So yeah, it's good to say a few things about the course. So we'll do magnetostatics. About 4 weeks, maybe 3 or 4 weeks. We may not do too much on material properties. Like remember in the first semester, we did electrostatics, and we also did a lot of how does an electric material work, like polarization of these materials. But in magnetostatics also, we would like to do the materials, but for time, we have to pick some topics. I may not do too much of magnetic material. And it's okay in the sense there is a course 575 by Dr. Mazumdar. He goes over it pretty much in detail. And if you're actually working in any one of the labs, I think it is probably necessary to know all those stuff. So I will surely say that if you're working in a lab, then you should take that course. If you're not working in a lab, probably you can survive for some time at least without knowing it and just getting exposed whenever you need to know. So that's magnetostatics. After that, we bring in release all the statics, right? So we do dynamics. Dynamics means we do everything, like all the 4 Maxwell's equations come together. Like electrostatics uses only 2 Maxwell's equation, magnetostatics uses the next 2. And this is when all of them come together. Again, this will lead to relativity immediately. So special relativity. If you have done classical mechanics before, then you have seen some form of special relativity. But we will do the electrodynamic version of it. It's pretty much the same, except that we want to see how Maxwell's equation fit in very well with special relativity. So we want to see all of what we did before this in the language of relativity. That means to say space and time come together there and how things work. So we'll spend pretty good time there. So that's another 4 weeks, let's say. And then we want to talk about scattering and radiation and scattering maybe. And that deals with the fact that whenever something is moving, and by moving, I mean accelerating, then a charge radiates. If a charge is accelerating, it has to radiate. So that's the connection there. And it not only radiates, it also leads to dissipation. So if it radiates, then it has to dissipate. It's like back reaction. Like if you're shooting using a gun, the bullet comes out, you invariably get a back reaction. And if there is an electron that's radiating, it's emitting photon, and it has to have a back reaction, and that back reaction shows up as a dissipation of energy. So that's a connection we will see. That will be very much in the end. And if time permits, we will also try to do what happened, it's the non-trivial statement is that usually we always say that nothing can go faster than speed of light. When we say those statements, it's a little not said very precisely. It should mean nothing can go faster than speed of light in vacuum. In a medium, light goes slower. That's what refractive index is. How much slower? That's what refractive index is. It's also slightly slower, and in fact, it can be significantly slower in certain materials in lapse. But then if it is slower than speed of light in vacuum, light in a medium goes slower than speed of light in vacuum, then there is a small gap there. And you can ask, in a medium, can some material go faster than speed of light in that medium? And that is possible. And that is what, whenever these kind of phenomena happens, like a very similar version is speed of sound. What if you go faster than speed of sound? How do things behave? And fighter jets usually can go faster than speed of sound. And that's what leads to what is called a shock wave. Sometimes when a fighter, if you've ever experienced, you just mentioned in the morning, right? Yeah, your relatives work for military, maybe you have some experience with being close to a fighter jet or something, or at least living next to it. And people, I have lived, and you experience sometimes windows break, like because of fight, if you're too close to the runway. And basically, it's a shock where there's too much of energy concentrated in a certain volume of space. And a similar version is all that is for sound, do the same thing for light. What if something, usually it's an electron, travels faster than speed of light in that medium? So light is slow and the electron is moving faster, then how will it behave? And that's what is called Cherenkov radiation. The kind of radiation that happens in there is called a Cherenkov radiation. Yes, Rob?
At one time, at the University of Missouri, Columbia,
Yes.
they would allow tours of the reactor. And that's how I first found out about that is I kept asking questions about the color of the water, because it looked like it had dyed blue.
Blue, exactly.
But it was the deceleration of the particles coming out of the reactor faster than the speed of light in water.
That's correct. Yeah, very good. Actually, I know that sometimes there is this SPS. What does this stand for? Students, physics students. S. What does the first S stand for? What does SPS stand for? Society of Physics Students. Yes, straightforward. They organize trips to labs close by. Sometimes they go to Oregon, sometimes to Oak Ridge, and sometimes they go to Columbia, University of Missouri, I think. And they have a, what's that, reactor? What do you call it? Nuclear reactor there. And typically in those reactors, particles go faster than light. In fact, that is a way, it has become a way of detecting high energy particles now, because they have a very specific cone of radiation that comes out. So it is a very clear signature of something going, some high energy particles. So sometimes you might have heard about a huge volume of water being kept as a detector. So what do they look for in there? They look for Cherenkov radiation in it. And a very signature visual effect is what Rob is saying. It is bluish, very like a glacier blue, kind of, very blue. Actually, I have never seen it. I've only seen pictures, so I shouldn't say. Yeah, I'm saying, and when I think of it, yeah, I never seen Cherenkov radiation. Radiated water, yeah, or at least I would strongly.
It took a while for me to get the explanation, because the person giving the tour was just a grad student in who knows what field. And so I kept having to ask questions. And I finally said, let's just assume I have a degree in physics. Who could explain this to me? And they found the professor, the physicist on duty, and he went through it, and I was amazed because I had never heard of that.
Yeah. It's cool. Yeah. I think I'm not very sure at this point, because this any of this kind of effect has this cone. Have you heard of the shock wave? Like whenever you have a shock wave, so there's something going in here, right? And so there's a cone behind it. but then I'm thinking a boat also has a cone behind it. And not only it has a cone, like it has a very specific angle, like the cone behind a boat is always exactly the same angle. I think some 22 degrees or 19 or 22 degrees. I think it's 19 degrees or something. And maybe there is this phenomena that the boat is going faster than the mechanical wave that can pass through that. So probably that's the same effect. And again, it's the same kind of effect that this is too much energy, right? That wave has too much energy. So if that comes and hits you, there's more energy than the other part of it. But check it out. I'm not very sure if that's the same. The wake of a boat is the same. Yeah, so we'll do. So broadly speaking, that's what we will do. So radiation, dynamics, and magnetostatics. Dynamics is best done in the context of special relativity. And special relativity, in what sense does the dynamics shows up? For example, let's say if you have a positive charge again. So if there is a positive charge, this is at rest, V equal to 0, that's the electric field. Right, standard electric field now. And we can ask the question that is there like you have yeah, so if there is a positive charge again, which is moving with a velocity v, let's keep it in the same direction. Moving with a velocity v, does this experience a magnetic force or not? So by magnetic force, I mean F is equal to Q V cross B. And you would say that it doesn't experience a magnetic force, right? There is a magnetic field in there. Like to begin with, this creates an electric field, it exerts a force on it. But there is no magnetic field, so there should be no magnetic force in there. But that's a relative concept in the sense that now this V equal to 0 depends on the fact that you're sitting in a lab where you're at rest with respect to this particle. If you start moving this way with a new velocity, V prime, right? Suddenly this starts to move with V prime now. This charge is no more at rest. And the moment this moves, this creates a magnetic field. Right? This creates a magnetic field, that means this will experience a force. So now there are two situations with respect to one frame. There is no magnetic force. With respect to another frame, there is a magnetic force. And in the first, naively you would say, oh, that doesn't make sense. Magnetic force, either there is a force or not. And it turns out it's a relative concept. Like force, as seen in this form, it depends on which frame you're. And then the question comes, okay, so if it is the case, so how does it transform? So what is the transfer? If I were moving, how does the force change? So we will see how electric and magnetic fields. So we usually in undergraduate physics talk about how velocities transform, right? Velocities add up in a different way in Einstein's relativity than normal Galilean relativity. But if we use that fact, electric and magnetic field are not unique anymore. Like it depends on which frame you're working in, and they transform in a certain way, and we will see those transformations. So can we? So that gives us an idea that whenever you want to do magnetic field, choose an appropriate frame. You can actually get rid of the magnetic field and get electric field. But that's not purely correct. you can get the other way also. You can kill the electric field and get magnetic field. So there are two unique ways. There's a pure electric field and pure magnetic field. They're distinct invariant quantities. And we will see what are the invariants. So usually what happens is that you're interested in knowing what quantity is invariant under or does not change under these transformations. And just to tell you what it is this quantity that doesn't change. If you were to calculate the electric field square minus the magnetic field square, this doesn't change in any frame you're in. So then it's a hint that, okay, that's a quantity you want to look for. So that's one, and actually there's a second piece, the dot product between them. This also doesn't change if between frames, between Einstein frames where one is going with respect to. That's just information just for your thought process. But we will derive those things by the end of the semester. And we will also know what kind of radiation is emitted when an electron or a positive charge is oscillating or accelerating in general. And that is the basic idea of how your cell phone works or how a radio works, of an antenna, basically. An antenna is antenna can either emit or absorb, in the sense either receive or emit. If an antenna basically is typically you just have a wire, right? So there is a charge in there. It's usually oscillating in there, and what kind of oscillation is going on in that decides what kind of radiation is emitted. Historically, one should appreciate these things in the sense Maxwell's equations came in 1865, and even though Maxwell's equation consists of four equations there, right? Each one of them was already known. Maxwell only changed one small term in the fourth equation, and right away it led to the fact that there is speed of light is possible. That is something that goes with the speed of light. And immediately that led to the idea that it radiates. If you move an electron, it should radiate, and that's a signal that goes faster. And within 1880, I think, with less than 10 years, probably 5 years between this, in the lab, you already had radio, right? The elementary form of radio, like, which we take for granted these days, like our internet, all depends on that. But right away, I put this as 15 years, but it started within 5 years, and but I think it was 1878 where really you could, from one corner of the room to the other corner of the room, you could emit and absorb. And within very quickly, like it was something like internet, that within 10 years you could cross the Atlantic, and it boomed immediately, and the rest is sort of, what it is. So that's broadly what we will do, but let's begin with magnetostatics. So let's write Maxwell's equations again. So in differential form, there is the Gauss's law, which we like to write it as epsilon here. And let me write, sometimes we also went into the Fourier space. So we went into the frequency space where time was, instead of time, we started writing frequency. That was only the last part of the semester. But let's come back to position and time, right? This is R and position time, and that's equal to charge density This is charge per unit volume. So the divergence of the electric field is equal to the charge density up to a constant, which is the permittivity of vacuum. That's if you want the Gauss's law. Similar, there's a Gauss's law for the magnetic field also. And what is that equal to?
Zero.
Zero. So it means that there are no magnetic monopoles possible. There are no north poles or south poles that can live on its own to our understanding ever. No. Third is L cross E. Now I expect that when I don't write anything, it's understood that that's position and time dependent. So word clutter, I stop writing it. And finally, L cross H is equal. So I should define what is D and F here. So D is E naught times the electric field, and D is equal to. They are identical in some units where epsilon naught and mu naught is 1. So, and what it, so Gauss's law was already there in the form of Coulomb's law. This is magnetic field, the flux of that being 0, that was known. This was Faraday's law, and this was known as Ampere's law, except for this term was not there. Ampere's law doesn't have this term. So that's what Maxwell found out. Maxwell realized that this term is necessary. And the moment you write this term together, all 4 equations imply that there is, it connects it with light. So the speed of light comes into our picture. So this is, this term is the Maxwell term, but we'll talk about that. Okay. Today, what we want to do is we already motivated how statics comes about from here. In the case of statics, any time dependence is not there. So you basically kill these 2 parts. So these 2 pieces are killed. And killing those 2 terms leads to the fact that electric field gets decoupled. Otherwise, this was a coupling part, right? Change in magnetic field can create an electric field, and change in electric field can create a magnetic field. So that coupling between electric and magnetic field goes away in the static situations. So let's do L. So this is static. All right, and that leads to electrostatics. So electrostatics. Which is basically L. And L cross E is equal to 0. Right? That's electrostatics. And magnetostatics is, so that's your first and third equation. And in this case, notice the difference between the 2. Del cross B is equal to mu naught times J. It's good to at this point remind ourselves of what is a divergence and a curl. If you have a vector field, if something is originating from a point, that's a measure of like a divergence is usually you have a point and there are field lines coming out of it. A point charge is a classic example. Like that's it is still divergence free everywhere except that point at the center. Right? If you're locally speaking, del dot of this electric field will be zero everywhere except at that particular point. That's what we learned. We emphasize that a lot in the first semester. So whenever you have this kind of fields, then it's an electric field. It cannot have any curl. Curl has to do with something going in a circle. Like magnetic field typically go in circles, right? If you notice magnetic field for a magnet, it starts from the North Pole and comes back to the circle. But that's a complete circle in the sense you will never see a magnetic field coming out from a particular point. You might say it is the North Pole, but the North Pole doesn't exist remember because of this circulation. So wherever there is a North Pole, that's immediately a South Pole also right at that point itself. So magnetic field lines somehow are constructed out of curl of an electric field. An electric field is associated with that divergence or something having a divergence instead of a curl. So that's a broad idea, and we want to. In the first semester, we talked about these two equations. How if you have a point charge, what's the electric field? If you have a line charge, what's the electric field? If you have a planar charge, what's the electric field? Those are the descriptions we talked about here. Very simplistically, we will do a line charge and if there is a ring of current, what happens and so on. So we'll do some very simple classic examples and see how it comes about. There is one thing that might be curious here as to when we think about current, we think about moving charges, right? But then we said we are talking statics. So there seems to be a slight confusion there as to what do we mean by moving charges when we actually have a current. In what sense is this magnetostatics? Where is the static part coming in there? So notice that. So where is the static part that went in here? We are saying that d rho by. So there is an additional feature here that d rho by d rho by dt is equal to 0. So charge density is not changing. So that's in electrostatics, that's implied in here. But what is the restriction on J, right? Is there any restriction on J? In what sense is this static? So let's look at that a little bit. So remember that, let's go back to Maxwell's equation. Let's remove, so to understand that, let's go back to Maxwell's equation and see what happens if we don't have statics. We know that current conservation involves, so this is current conservation or charge conservation, right? Not current conservation, charge conservation. How would you derive charge conservation? So that's charge conservation, which basically says that the time derivative of charge density plus the divergence of the current density is equal to 0. Right? That was one of the conservation equations we derived last time. In this case, this should be interpreted, J is interpreted as a flux of charge. Remember, if you were to integrate this, the rate of change of charge in a per unit volume is equal to the how much charges are going out of that volume. So in that sense, this is a flux of charge. How would you derive this? we start with the first equation because that has a charge. Take the time derivative of this. So this is d by dt. So I'm starting from this equation. So that's dotted with epsilon times E is equal to d rho over dt. Right? So that's a true equation coming from there. And if I do the same thing in here, take a divergence of that equation. So that's del dotted with del cross H is equal to del dotted with d by dt of epsilon times E, right, plus del dotted with J. Right, that's from the first equation, that's from the fourth Maxwell's equation. Notice that this is equal to 0 because of the vector calculus that this comes as an antisymmetric product. And these two are identical because the gradient and the time derivative can be swapped. So these two cancel out. And if you add these two equations, you get d rho over dt plus del dotted with J is equal to 0. And that tells us, now we interpret what happens in statics. Like in statics, we are saying that this is equal to 0. What is the constraint you put on the current? It is that the current should be source free in the sense that its divergence should be 0. So in statics, so whenever we do statics, is this readable? Yeah, in statics, you would put d rho over dt is equal to 0, which immediately, because conservation of charge is a fundamental equation, this immediately implies that the current that we talk about has to be having no divergence. Broadly, what that means physically, that means it is steady currents. Current should not be changing with time. So steady currents are okay, and it shouldn't have a source. Like it shouldn't suddenly appear from nowhere and end nowhere. Usually you will have either circular currents. So this means that no change in time. So these are called steady currents. Steady current. That's a language used, but what do we mean by that? It doesn't change with time. Current stays the same. You can have a loop of current, or you can have a current carrying wire starting from infinity and going all the way to infinity. That's also perfectly fine. So magnetostatics, in that sense, then is described by these two equations and the fact that the currents is steady, or we say it is divergence free. Okay, there is also one more thing I should point out here, because the moment you write a conservation equation, it brings out the idea of flux. And I think I should point out that, so what is flux, by the way? How do you define flux?
It's kind of like the rate of change into or out of a particular enclosed volume.
Because that's the way I have been emphasizing very much. That's correct. Have you seen any other definition of flux from your electrostatics? Flux of electric field, how do you define flux of magnetic field? How do you define that? So I think there are two definitions I looked up, and so this can be a quiz, right? So that's a quiz. Define flux, look up. And there are two definitions of flux. The first definition is, let's say, flux of, we could say, magnetic field, right? Flux of an electric field, let's say, is equal to, you have an area A and dA dotted with electric field. Is that clear? Like in Gauss's law, when you say that the electric field is going across the area, so then you say this is the flux of the electric field. Is that familiar, right? So how much electric field? So you would say there is an area there. So that's your dA, and electric field could be going this way. So you take the dot product of the electric field with respect to the area vector and sum it over everywhere on that. So, and that's what we learned. But then I also introduced that if you have a chart, for example, in this equation, so this is d rho over dt. That's what Moses just now was explaining. So that's del dot J is equal to 0. This means that if you have a volume, so this is a sphere or a volume, so this is that's a three-dimensional volume. J here is thought of as flux of rho. Like whenever you have this equation, this can be interpreted as a flux of the quantity that's changing. So usually we think of it as if you have a country, the population change is equal to the how many people are dying or being born, plus how many people are crossing the boundary. So and that's the flux. So this is in fluid dynamics. Like in fluid dynamics, there is a water coming in, going out. So what's the flux of water or amount of matter you can think of? But this is not the same as this second one, right? There's a difference here, or at least I don't see a connection directly. I think they are two independent definitions, but they're closely related. For that matter, one is a vector and the other is a scalar, right? So it seems like it should not be the same. So that can lead to confusion. Be aware of that. But anyway, so what's the quiz? Look up the definition of flux and highlight this difference. Okay, so that's electrostatics and magnetostatics. So let's actually go to this side of the board. Okay. Yeah, so let's quickly recap electrostatics. Because we want to do magnetostatics very much in the spirit of how we did electrostatics. So of course we are saying that is charge is not changing with time, so it is statics. Right. And then there is this equation you have dotted with E is equal to rho over epsilon naught, and del crossed with E is equal to 0. And notice how we operate there. We say that, did we lose someone? Michael got disconnected? Okay. Okay. Since this is curl free, we claim that this implies that the electric field can be written as a gradient, and we just choose it to be negative of that. This is the voltage that you measure, like in introductory physics, the electric potential. So electric field can be written in terms of the electric potential whenever the curl of the electric field is zero. It's like the idea of a conservative force in classical mechanics. And the moment you have this, go back in here, this implies that we substitute this here, so that's L square phi is equal to rho over epsilon naught. Right, that's the couple of steps that comes in. This implies that there is a potential. If there is a potential, this equation has to be satisfied. And this is a Laplacian, and we saw that Laplacian can be inverted. We introduced the idea of a Green's function. The inverse of the Laplacian, in the sense if I had to put this Laplacian on the right side, then I can get the electric potential. That's basically the Green's function. And this implies, so this is a solution if you want, so this is the most general solution. Electric potential everywhere in space, there is no time, because it's statics, is, since this is the Laplacian, the inverse of the Laplacian is 1 over r minus r prime. That's 1 over, that's 4 pi epsilon naught, and that is d cube r prime and rho of r prime divided by r prime. Right. Notice that this uses the fact that minus L squared, so the inverse of this, notice that's an inverse operator of the Laplacian, is equal to 1 over 4 pi times 1 over r minus r prime. That's like lots of information. This is kind of a recap of what we did in the last semester. So the inverse operator for this is equal to this, then you get this expression, which is basically saying superposition principle, right? In elementary introductory physics, we say if you are given charges Q1 plus Q2 plus Q3, and that's the electric potential due to the first charge, electric potential next charge. So each charge adds up. So this is the adding up with the superposition principle. That gives you your electric potential. Once you have the electric potential, take the gradient, you get the electric field. Right? So you can say this is your, if you want, this as your starting point. Once you have derived this, you say this is your starting point. Give me a charge density. Complete this integral. You'll get the electric potential. Take the gradient, you'll get the electric field. If you want the force, that force is charge times the electric field, and then you will have everything. Okay. So that's the, if you want a summary of electrostatics in the very basic sense. We want to do a similar thing for magnetostatics. Now let's do magnetostatics. Instead of rate of change of charge density being 0, we have the currents are steady, which means that their divergence less, if that is known. Divergence for the current density, and the Maxwell's equation, or this time it's the opposite, right? So this is B is equal to 0, and del cross B is equal to mu naught times J. right? That's the difference, and you immediately say, oh, we cannot do this anymore, right? E is equal to del of phi, but we still have divergence free. If a vector field has no divergence, what can you say about the magnetic field? What kind of expression can it obey? So this implies that B can be written as, like, it's not a solution in the sense you're writing one vector in terms of another vector, but you bring out some properties in it, and you say that it has to be a curl of a vector field. Notice here, because the curl was 0, electric field could be written as a gradient of a scalar. Magnetic field, because its divergence is 0, can be written as a curl of a vector field. So this is called a magnetic vector potential. Why is that possible? Because it satisfies this identity. So let's do that quickly. So let's check that. Right? Let's put this in this sort of immediate. What is that equal to? Right. Divergence of a curl of something. What is that equal to? Is your vector calculus? So think of it as Lewis-Civita symbol. There's a dot product first of all. So let's use index notation, right? So that's del I and del cross A of I. Right. So this is index notation, which says that there's a dot product, there's a summation in I going from 1, 2, 3. But this is a curl, so that's also can be written as I epsilon I j k. Remember this? This is del G. But now notice that I can replace, it's better if I write it in this form. So I can move this because these are numbers. This is a partial derivative in x or y or z. This is another partial derivative in x, y, or z. And they commute, right? If I take a partial derivative with x and a y, which one I do first doesn't matter. But so if I interchange I and j, nothing changes. But if I interchange I and j here, it changes the sign. So this is anti-symmetric in I and j, that's the line width. This is symmetric in I and j, that cannot survive together, so that's equal to 0. One can show this more formally, but that's equal to 0. Okay. Often you say whenever the gradient operator comes as a curl and a dot together, it's always 0. Here also it's the same thing. What happened there? Here a curl and a dot, or curl of a two gradient operators is equal to 0. So that's so if you have a magnetic field, you can in magnetostatics you can always write it in as a curl. In fact, the same thing works with electric field also. You cannot see there. Yeah. In electrostatics, electric field can be written as a gradient of an electric potential. This is an electric potential. Electric just to write it in this form, scalar potential. So electric field in electrostatics can be written as an electric scalar potential in this form. Magnetic field can be written in terms of a magnetic vector potential, and it is written in terms of a curl. Right? That's okay, but what if you release the statics form of it? Right? It's a good idea to, at this point, just to mention at least that what happens if I were to not talk about statics. Is this still valid? Right? What happens to this in the case of statics? Right? This equation is still valid. Right? So this is still true. Even if I were to release the idea of magnetostatics, this is always true. This is not true because this equation fails. So this is no more true. In fact, what happens is that this quantity comes in there, right? It is not obvious here. So this is the extra piece that shows up. And if you were to release statics, then I said that we will get away from statics 1 month down the line. That term will shows up. But in statics, this is not bad. Again, time derivative, right? So it's clear that that's what's not there. So we have this curve of a magnetic field. Any questions at this stage? So then again, we want to follow this through. Now that magnetic field is a curl of a vector potential, put it back in the other equation, we should get a differential equation. And then that should give us magnetic field. So let's try to go there. Okay, so again, we did magnetic field. Divergence of the magnetic field is equal to 0 implies that can be written as a curl of a magnetic vector potential. The second equation told us that the curl of the magnetic field is equal to mu naught times J in the static situation. Otherwise, there is one more term in there. Substitute this in this. So it's del cross great. So that's your new equation. Earlier in electric field, that was a Laplacian, but this doesn't seem to be a Laplacian immediately, but we can process this. And the process is that use the vector identity, right? So this is equal to using the vector identity for gradients. This is again the Laplacian of the electric potential mu naught times J. It does come up, the Laplacian comes up, but there's this extra term that floats around. But notice that whenever you write something as a derivative, there is what is called a gauge freedom that you have. So at this point, you choose a gauge. Again, we saw this. Choose a gauge. What does a gauge mean? When we are talking about electric potential, we often, like if you're doing electric experiments, we often say that we have to ground it, right? That is a reference for the voltage. So we have to ground it, and then with respect to the ground, You can choose the table to be your ground, or you can choose infinity to be your ground. The various references possible. Now, in this case, we have a vector potential. Is there a similar dependence freedom there? And yes, there is a gauge freedom. And you can choose that to fix once, only once, you can choose this. It is okay to choose this to be 0, and then we have to verify that all our solutions are indeed satisfied. That's not very obvious here, especially the fact that the choice is not. Is it possible or not? That should be checked. And this is called the Coulomb gauge. And we will use this gauge all through and magnetostatics. So we should immediately check that whatever answer we get, it actually satisfies the Coulomb gauge or not. And that will be, we'll try to do it here, or it's also part of your homework, so that you got to check this. But for now, if we have that, that simplifies a lot, because then you can almost immediately choose, or not choose, use the electrostatics result. So if we use this, then we have this in here, and again we see the Laplacian in there. Whenever there is a Laplacian, we can invert it. Right? And the inverse of a Laplacian we saw is 1 over r minus r prime. Right? So invert it here. So this is the Laplacian. Negative of that, move it to the right side. That becomes an inverse. And remember, negative radian squared inverse is equal to 1 over 4 pi r minus r prime. And use exactly the same idea as electrostatics, and we can immediately conclude mu naught over 4 pi so very much like electrostatics, each piece of current has an electric potential. Now it is, sorry, it's a magnetic potential now. Earlier it was an electric potential. Each piece of charge density contributed an electric potential. Each piece of current density contributes to a magnetic potentials, and it satisfies the superposition principle. Notice that the magnetic vector potential is in the direction of the current itself. So if you have a current carrying wire, for example, then usually what is the magnetic field associated with this? With the current carrying wire, right? Circular type. So this is the magnetic field associated with this. So that's in one plane and everywhere around, and it decays off as 1 over r there. But we haven't reached the magnetic field. We don't know the magnetic field expression yet, but we know the vector potential, the magnetic vector potential, that's in the direction of the current. If all the currents are in the same straight line, A is in this direction. So this is the current carrying wire. So that's your J, and the magnetic vector potential will be in this direction like this. That's your A. Okay. So usually they are in the direction of J, but they're spread out. It's not like current is only inside the current. This is like a field, vector field, right? So this is a field, and you should start visualizing what this field lines are for a particular geometry. And we will come back next time and do how to get the magnetic field from here. So maybe so we can just, so B will be equal to del cross A. So I'll substitute this and process a few things, but we'll come back next time and process that. And then do examples, like we can do a lot of examples as to do this, do that. And that's what your homework is also. And in half of your homework is about verifying that, start from here, verify that this is equal to 0, start from here and verify that this is equal to 0. And few, I think there are some 4 or 5 checks you have to make. Formal checks, it's not a particular problem. As we'll see next time, there are standard ways of doing that. So we'll see that. And then doing specific examples, like in your homework, it is again a line chart that we deal with. And we will also do circular ring of charge. Okay. And I'll stop with this. Yeah. So little dense for a first class, but then yeah, we'll reach that. Yeah. How is everyone? Did you guys go around by any chance? Anyone traveled or got to travel? Like, I don't know. No.
Small amount.
Small amount.
I was in St. Louis most of the time. I took a small trip to Kansas to visit a friend.
Yeah, that's good. Okay, that's,
I was in St. Louis at a point in time,
Yeah.
right after Christmas.
Okay.
I figured since my wife and I were both immune, we might as well take advantage of it.
yeah, good. That's fair. Actually, saying that I was also there in St. Louis right after Christmas and New Year. One of my friends, they expected a baby and they needed some help.
Mhm.
So I did some babysitting here. So,
Gotcha.
Probably we were in the same area.
Mhm.
And sometime.
We got a real good deal with the Weston.
Okay.
That's the one right next to the Bush Stadium.
Yeah. Nice.
Cool.
Very cool. What did
Because
you
they're really desperate right now for customers.
Yeah, I'm sure.
That's right.
How many days did you spend in St. Louis?
Just a couple.
Uh-huh.
3 days, 2 nights.
That's cool. What were you able to do during that time?
Oh, it's really a little shopping, relaxing.
Uh-huh.
Saying, it's like holidays are over, we survived.
Yeah. For sure.
Okay. That's, yeah.
Did you do anything, Dr. Shadish?
I was mostly here. Yeah, worked a little. It's a good time to work.
Mm-hmm.
That sounds like it's okay. But yeah, relaxed for sure.
Mm-hmm.
Catch up with my relaxation.
It's surprising how many people were here over the break. I made a couple trips down and there was never an empty parking lot other than the apartments and stuff.
Okay. Yeah.
And that was right after New Year's, before anything had back up.
Mm-hmm.
Sure. What about you guys? Luke, you must have gone home, right? It's close by.
Right. Yeah, I was just home for the break.
Aliyah probably stayed here. That's my guess.
Yes, for sure. I just spent good time with my kids.
Yeah. Jordan, you there? Or you have to leave? Jordan is quiet today. Okay, so nice to see you guys again.
Yeah, good to see you too, yeah.
Yeah.
So,
Yeah.
we'll
Okay.
see you Thursday.
Yes.
good.
Such a shorter period between classes.
Right.
Yes,
Right,
correct.
right.
Last time we were meeting every day, like spread out. This is different here. Okay.
Okay, Dr. Shajir,
Yes, Salia.
if you don't mind, I have a question, but not in your course. I want to
Mhm.
ask about, can I ask the other student?
It's up to you. I mean, if you feel comfortable, you can ask. If you want to wait, you can wait for others to do. It's up to you.
Yeah, okay. For those who register for quantum, I didn't understand. Do we have to come to the university, or because it show two type? It's the normal one and the other one it's hyper. So I don't understand that first.
Oh, you're asking whether for when you look at the schedule, it
Uh-huh.
says meeting the actual schedule, and then it says hybrid.
Yeah.
What that means is that the teacher decides, the instructor decides what's the process. It typically means that there is a good online part of the course, and you might be asked to come to the university for exams or something like that. So I would say wait for the instructor to put in the syllabus. Has the instructor given you the syllabus?
I just registered last night. I don't know if he.
Yeah, so probably most of the instructors wait until the last moment. At least I am like that. Like I'm 1 hour before the course begins, I upload it. So if you wait for the first class to begin, you should have a clear understanding of what the expectation is. Did I answer your question?
Yes, yes. That
Yeah,
you make.
so the
Alia,
first,
is that 5:30 A?
Mhm.
Yeah, today we're meeting online. I think Rob and I got an email, but I can forward that to you.
Yeah. Thank you, Luke. Thank you.
okay,
Because I
that's
just
good.
registered late.
Yep, no problem.
Okay, that's a clear answer. Perfect. Okay.
Yeah, thank you so much.
Yeah, helps to have the question in front of everyone. Good.
Thank you.
Okay.
Have fun in quantum, guys.
Thank you.
Whatever you want to do.
You finished, Anna?
Yeah,
Okay.
you'll survive.
What time is this class?
4 o'clock.
4?
4.
4. Okay. Okay. Sounds good. Okay. Enjoy, guys.
Well, thank you. You too.
Yep.
Yeah. Okay.
See ya.
Bye.